Hello everyone, welcome to this class E279AS on the concept of signal integrity and power integrity. So let's first talk about what we're trying to do here. How is signal integrity and power integrity applicable to packaging, and what exactly do they mean? So first, let's talk about signal integrity. So signal integrity basically has to do with the quality of signal transmission through a link between a transmitter and receiver. So, for example, consider two chips. Say there's chip 1 and chip 2. Assume chip 1 is, these chips could be either on the same package or they could be on different packages which are present on a PCB. And chip 1 has to communicate to chip 2 through a link. So basically, there will be a transmitter on the chip 1. And we'll talk in more detail later on in the course how the transmitter actually looks like, and how the transmitter also sends signals on the link. So the transmitter sends the signal through a link. The link could be a PCB trace or some other kind of metal wire that basically carries the signal, and then finally the signal goes to the receiver on chip 2. So usually as you know, most of the electronic systems today are digital. So the signal at the transmitter side, so let me draw the signal in red. So signal of the transmitter side would basically be some digital signal, as you can see here. So maybe this is 010100, and then as this digital signal basically travels along this transmission line, and we'll talk later about what a transmission line is. But as the signal travels along this link, there are several different kinds of effects that happens that basically distorts the signal. So, for example, that any signal, no matter what kind of nonlinear or linear signal is, can be decomposed in its Fourier components. So, for example, this digital signal would have some fundamental component and then some higher frequency components. So what ends up happening is that each one of these frequency components, say this is frequency omega 1, omega 2, and so on, what ends up happening is that each one of these frequency components behaves differently in the link. The attenuation or the reduction, the amplitude of the signal as it goes from the transmitter to receiver changes with frequency. And also each one of these signals can be shifted in phase as it travels along the link by a different amount. So once the signals go through the link, each one of these signals could be, say the omega 1 has been reduced in wavelength, reduced in amplitude, omega 2 has also been reduced in amplitude and shifted slightly, omega 3 is also, and so on. So once you add up the signal at the receiver, you end up with a distorted digital signal, maybe something that looks like this. And say originally you had sent 0 1 0 1 0. In the end, because these signals are distorted, when the signals are sampled at the receiver side, maybe a 0 got flipped to a 1 or a 1 got flipped to a 0. And so you can get basically bit errors and also other effects such as timing errors and so on, which we'll talk about later happens. So signal integrity basically deals with how, once you send a signal in the transmitter side, how well you can recover back the original signal so that you can minimize these errors in the data that you send, and also other timing related issues that we will talk about. So that is basically the thing we are going to talk about, in signal integrity. And we are particularly going to see how to design this link as well as how to design the transmitter and receiver so that you can minimize these errors in sending the data along the link. What about power integrity? So, power integrity is often thought with signal integrity because they are quite interrelated to each other. The main idea behind power integrity is how well you can send power to the chips. So, let's consider our original case. You had chip 1 and chip 2. So, both these chips have some kind of circuits on them. Could be digital circuits, could be analog circuits, doesn't really matter. But these chips basically require some power. And this power is sent at a certain voltage. Say for example, PWR is the uh, power voltage and then a ground voltage. And then this power and ground is sent to all the chips. And so now you can immediately see a problem that could happen is say you are sending the power through this terminal here and getting the ground signal from this terminal. Because of the resistance of these whatever these metal wires are that carry the power and ground signal, the voltage that chip 1 receives and the voltage that chip 2 receives can basically be different because of the resistance drop along the link. And hence the power, the voltage differential that is delivered to chip 1 could be reduced and chip 2 could be reduced even further, and therefore and that affects the performance of the chips. There are also other effects, which is usually this power is not, even though you're sending a DC power, it may not be a constant level. So, for example, here the DC power could be noisy, and the ground could also be bouncing up and down and noisy. And if this power link here also has an inductance, then these variations in the voltage create a variation in the current, which can basically also cause, because of the inductance, can also cause voltage variations at the power and ground terminals of the two chips, which can also affect the performance of the chip. So power integrity basically has to do with how we can design these so-called power planes, or the power and ground connections, how we can design them so that each chip basically gets a good quality of power in terms of the voltage it gets, as well as the allowed fluctuations in the voltage. So that's basically a summary of what we are trying to do by doing the signal integrity and power integrity. So now, in order to understand, so we are first in the first few classes, I think 2 classes, we are going to particularly focus on signal integrity. And then after that, we will move on to power integrity. So when we talk about signal integrity, one of the main important concepts in signal integrity is the idea of what a waveguide is, what a transmission line is, and when to model a given link as a transmission line or to model it as a lumped element, such as a resistor, inductor, or capacitor. Excuse me. So, in order to understand anything about signal integrity, first we need to understand how electromagnetic waves actually behave in a suitable communication link. And the fundamentals of understanding any electromagnetic phenomena depends heavily on your understanding of the Maxwell's equation. So let's talk a little bit about Maxwell's equation. We won't go into too much detail, but then just qualitatively, if you understand it, then you can also understand how these equations behave. So imagine that I had a charge, say there was a positive charge. We know from Coulomb's law that if you have a positive charge, then the electric field that is produced by this charge goes radially outward, as can be seen here. And not only does it go radially outward, the strength of this electric field also falls as 1 over the square of the distance from the point charge. So mathematically, we know that the electric and magnetic fields, they're called fields because they are present at every location in space, and they're not only fields, they're vector fields, because at every point in space you basically have a vector. So the electric and magnetic field is a vector field. So at every point in space you basically have a vector that shows you the magnitude of the field and the direction in which the field exists. So when you consider any vector field, there are two kinds of possibilities of the way they can be. So one is they can diverge. That is, say the fields are something like this. So they are either diverging out from a point, or they can diverge into a point. So this is one possibility. The other possibility is that the fields don't diverge at all, and they can just circulate, as can be seen here, about a point. So when a field diverges from a point, you can mathematically represent that quality of the field by an operator called this divergence operator. So this is represented by the divergence of, say, the electric field, and this is represented by the so-called curl of the electric field. So by getting equations for how the divergence of the field depends on the source, for example, the charges, and how the curl of the field also depends on its own sources, you can get an idea that depending on any condition, how the electric field actually is throughout space. So that's basically like some basics of what vector fields are about. But let's go back to our case where there was a point charge. So here you can see clearly that if you had a point charge, the field diverges. So this is mathematically represented by the fact that the divergence of the electric field is equal to the charge density, which is present, which is basically causing the field. Similarly, if you look at a magnetic field, so imagine you had a wire that was carrying a current. The wire, as we know, creates a magnetic field that basically loops around the wire, as can be seen here. And if you look at how the field is, this is basically a field. So this is, say, the magnetic field, which is represented by field intensity is represented by H. And if you look at how the magnetic field is in the cross section of the wire, you see that it kind of, if this was the wire cross section, this field basically circulates around the wire. So mathematically, you can represent this as the circulation of the H field is basically the electric current J. But this equation gets a little bit more modified because if you consider, so let's consider a situation where you had this wire that's carrying a current I that is time varying. And say for some reason this wire terminated at a capacitor and then the wire continues later. We know that if you send a time varying current, such as an AC current on one side, this current just, the capacitor basically just shorts the AC current, and so the current just continues to flow in the wire. So, although you technically have no physical connection here, you do have a continuity of current that is going along across this capacitor. So physically, if you look at what's happening inside the capacitor, you basically have the capacitor charging and then discharging. So there's an electric field that is set up inside the capacitor, between the capacitor plates, that is varying with time, which can be represented by this. So there's a time varying electric field times the dielectric constant, which is the dielectric constant in the between the capacitor plates. And so this time rate of change of electric field also behaves analogous to the current that was carried in the wire because of current continuity, and it can also generate this curl in the magnetic field. So we also have to add this term to the equation. So you get del cross E is the conduction current J plus this time rate of change of electric field also causing the curl of the magnetic field. So now we have basically we have two Maxwell's equations. And also we have a third one, which is basically because the magnetic field always curls, the magnetic field never diverges. So the divergence of the magnetic field is also zero. Uh, and finally, we have one more equation which has to do with the electric field. So imagine you had a loop of wire, as can be seen here, which is placed between two poles of a magnetic, basically two poles of a magnet. And let's say that this magnet was generating a magnetic field that was varying with time. So let's say this magnetic field was varying with time. Uh, then what we basically find is that this time varying magnetic field that cuts across the loop basically sets up a current in the loop, as can be seen here. And this current in the loop is set up in such a way that the magnetic field generated by this current in the loop opposes the original applied magnetic field. And this is basically called as Faraday's law of induction. Um, and it was originally discovered through experiments. And so mathematically, what exactly is happening here is that this time varying magnetic field, so if I look at the wire itself, this time varying magnetic field that is passing through the wire basically sets up a circulation in the electric field along the length of the wire. And this circulation in the electric field basically generates a voltage along the length of the wire that sets up the current to flow through the wire. So mathematically, now we know that the curl of the electric field is basically generated by a time varying magnetic field, and the negative sign basically indicates that the electric field curl is set up in such a way that the currents generated by this curl in the electric field basically opposes the original applied time varying magnetic field, which is often called as Lenz's law. So now we have the four Maxwell's equations. At least, I mean, if you, even if you don't understand it deeply, at least from a qualitative perspective, you understand what they actually mean. So you have the divergence of the electric field is basically the charge density, the divergence of the magnetic field intensity is zero, and the curl of the electric field is the time rate of change of magnetic field, and the curl of the H field is the conduction current plus the displacement current. So these are basically the four Maxwell's equations. Now, these equations, which are basically very general, they apply to any system. They apply to electronics. They apply to a transmission line. They apply to antennas, and they really apply to any kind of electromagnetic phenomena that you can have. But what we are going to particularly use them here is to understand how a signal propagates along a link between, say, two chips, and the link usually is a transmission line, and we'll talk later about what a transmission line actually is. So now, if you look at these equations, right? So you have if you look at these four equations, something very interesting happens with these equations. Is that imagine you had a region of space, right? So imagine you had a region of space. So let's say some region of space that had some dielectric constant epsilon and some permeability mu, which are the properties of that space. And let's assume for now that this dielectric constant and the sorry, not yeah, the electrical permittivity as well as the permeability basically are constant throughout the space. Let's also assume that the space does not have any charges or currents in it. So there are no charges in this region of space, and there is no currents in this region of space. So if we simplify this Maxwell's equations within this region of space, then we get the equation that the divergence of the electric field is zero, the divergence of the magnetic field is zero, and the curl of the electric field is basically minus mu times del H del T, and the curl of the magnetic field intensity is just going to be epsilon dE dt. So now what you can do is, in this kind of situation, you can actually combine these four equations by doing a curl on the curl. So if you do a curl on the curl of the electric field, then from vector identity, we know that this is just the gradient of the divergence of the electric field minus the Laplacian of the electric field. So how this comes, you can basically refer to any vector calculus book, but this is just a vector identity. And this is equal to curl of, so basically what was in this equation, which is minus mu dH dt, which is just minus mu d dt curl of H. Why you can go from here to here is because del and ddt are independent of each other, so you can change the order in which you operate. So, and what do you know? We know that the curl of H is basically epsilon dE dt. And on this side, you know that this is del gradient of del dot E minus Laplacian of the electric field. But we know that del dot E is zero because there's no charge density in this region of space. So this is zero. So you get minus the Laplacian of the electric field is equal to minus mu epsilon of the second derivative of the electric field with respect to time. And if you take the electric field to the other side, you get del square E minus mu epsilon d square E over dt square is equal to zero. And so if you do the same thing with the magnetic field, you get another equation, which is del square H minus mu epsilon. Yeah. So if you had a region of space, so what we basically have here is we had a region of space where there was no charge density, there was no electric current, and had a uniform dielectric permittivity as well as a magnetic permeability, then in this region of space, you can combine the four Maxwell's equations to get these new set of equations. And if you look at these equations, these are basically wave equations. They basically indicate that the electric field and the magnetic field are propagating through the space in a wave-like fashion. And any solution of this electric field has a form that the electric field at any given position and time can basically, so let's be more general here. So you will, if you solve, no matter what the electric field is, doesn't matter what shape it has, if you solve this equation in a region of space that I mentioned here, then the electric field at any position r and any time t will be of the form, will be some function of basically some dot product of something called the wave vector dot r minus omega t. So it will be of some form of a wave that is basically propagating along that is basically propagating in this medium. So this is basically describing that there are electromagnetic waves that is traveling in this medium of uniform permittivity and permeability. So now, before we move forward, so yeah, one second. Let me make sure I've covered everything I need to cover here. Yeah. So as you know, so this function, right? So this function k dot r minus omega t, what it is basically telling you is this. So imagine you had this region of space that we were originally considering of uniform dielectric permittivity and permeability. So imagine you were having an electric field here at some location r and t, and let's say you are observing, say within some radius away from this point. Say this was a point that was located at location r prime at a at the same time. Then what you notice is that the electric field at this location, so the electric field at the location r prime and t, will actually depend on the electric field at r, but at a certain time, which is basically delayed by the distance between the 2 points. So if say the distance between these 2 points, this radius is L, then it depends on the electric field at location R, but delayed in time by L over the speed of light, where c is the speed that it takes, or the velocity that it takes for the signal that is located at RT to propagate to R prime T prime. So this, as we will see later on in the course, this actually has a lot of implications for what kind of model we use to understand our link. So whether we go for modeling it as a waveguide, or we go for modeling it as a transmission line, or we can go to model it directly as a lumped element. So that really depends on what is the wavelength of the signal compared to the dimensions of the link that is actually carrying the signal. So now, before we move forward, let us talk a little bit about how we would propagate energy. So what the communication link actually does is it's basically propagating, or it's basically sending electrical energy from one chip to the other. So let's try to understand how we would uh, basically transmit energy from one point to the other. So sometimes electromagnetic fields can be a little difficult to visualize, but because we are talking about wave phenomena here, you can use an analogous system to understand how the wave behaves. So one analogous system that I like to use to think about how the electromagnetic field behaves is to consider water waves. So imagine I had a pond. Okay, so I had a big pond. So imagine this is an infinite pond, so it extends all, and I'm looking from the top view, so it extends all over space. And then imagine you're looking at the surface of the pond. So let's say I throw a stone at this location S. So the moment I drop a stone at the location S, you're going to have water waves that are basically going to propagate out, which are going to propagate out spherically or circularly, as I can show here. And let's say I had a piece of paper at some location, which was, say, located at a distance, say, L from the source. And let's say I was monitoring. So once these waves propagate, if you look at the paper, and if you were to plot how the paper moves up and down on the surface of water, the paper would basically move up and down with a certain amplitude. And let's say that the amplitude that it moves up and down is represented by h of t. So this is a time varying amplitude. Sorry, it's a time varying distance up and down. And it has some amplitude, and it has a certain frequency that depends on the frequency of the wave that was generated, right? So if you had this situation where I just dropped the stone and I was looking at how the paper moves up and down, it would move up and down sinusoidally, as can be seen here. And what you will find is that the amplitude, so the maximum height and the minimum height that this paper goes up and down, depends on the energy with which, or the power with which the stone was actually thrown. So if you throw the stone harder, this paper you expect would move up and down much higher. And it's also inversely proportional to the square of the length between where the paper is and where the stone was thrown, right? So, even though what is it saying is that when I threw the stone inside the on the in the water, the energy of the stone, the kinetic energy of the stone was basically used to excite waves on the surface of the water, and because these waves are moving spherically outward or circularly outward, the energy of the wave is basically sort of dispersed throughout the area, and so the amount of energy that the paper gets is a small fraction of the actual energy that you send. So now imagine I wanted to increase the height. If I want to increase the oscillation height of this paper, what can I do? So there are two ways to do this. So consider the same situation. So now, if I wanted to make sure that all the power that I generated by throwing the stone goes to the paper, what can I do? So one is I can create a wall. Like for example, if I create a wall like this, then what happens? So the stone is, when I throw the stone, it's going to create these water waves that's going to travel circularly outwards. But the moment it hits the boundary of the wall, it's actually going to reflect. So it's going to reflect like something like this, and from bottom also it's going to reflect. And these reflected waves now propagate like this, and they go bounce back and bounce and keep bouncing, and this one goes on. And these bouncing waves eventually will reach the paper. And the paper now, if you look at the way the paper oscillates, the paper is now going to go up and down by a much greater amount. And you will find that the amount by which the paper goes up and down not only increases, but if I plot the height, it's now proportional to the power of the source, but it no longer has a dependence on the distance of the paper from the source. So if the distance was originally L, in the original case, you had a 1 over L square, but here it only depends on the power at which the stone was thrown and no longer depends on the distance between them. The reason is because the power is basically being guided by the walls. So these walls are essentially guiding the power down the line so that all the power now reaches the paper. So, if you were now to go back to the electrical system, if throwing the stone into the water is analogous to a transmitter sending the signal, if you now can confine the signal within a certain region of space, just like how I've confined the water waves within a certain region of the surface of the water, I can make sure that most of the power, or almost all of the power from the source, ends up in the receiver. And no matter how long I make the receiver or how far I make the receiver from the source, you can make sure that almost all of the power reaches there. So this is the concept of the waveguide. So this thing is basically called as a waveguide. So if you look at this water case, so this is one way to make it, but there are many ways to make this waveguide. So another way you can think of is, imagine I had basically throwing the stone in the water. But now, instead of having a wall in the surface of the water, imagine I could somehow create a flow. So I would create, like, for example, two flows. So here, say I create a flow of alcohol up and down. So I would basically flowing alcohol here. And now I have the paper here. In this case, what happens is when I throw the stone, it creates these waves. But when the waves go and hit the surface, the boundary of the alcohol and water, some amount of it basically goes into the alcohol, but some amount of it, depending on the angle at which it hits this interface, some amount of it basically is reflected back into the water. And this reflected wave goes to the next interface and is again reflected and then finally reaches the paper. Of course, some amount of them do pass through the alcohol, but there will be a certain percentage or a certain fraction of the generated power at the source would be guided within the water and would reach the paper. This is another way for you to guide the energy in the paper. But here, of course, if you look at the height at which the paper moves up and down, so this height would not be as much as the case where you use the wall, but it would still be much greater than the case where you had no flow of alcohol. So in this case, it will be proportional to the power, but it will be also proportional to the square sine square of the angle that is made by this. Basically, this is called the acceptance cone. So within this angle, as long as the waves are within this angle, it is basically guided within the water. But if it exceeds it, it goes into the alcohol. So it's proportional to the square sine square of this angle. And again, here it doesn't really depend on how far the paper is from the source. So these are two ways of that by which you can make a waveguide. So if you look at the analogous situation in the electromagnetic field, what the first case with the wall is analogous to having an electric field confined within two metal plates. So there'll be two metal plates, and the electromagnetic field is basically bouncing between them and is confined to them. So this is analogous to the case of the wall. And the second case with the alcohol, which is basically what was happening in that case, is you had two materials of different viscosity. So you had the water having a higher viscosity than the alcohol. And so analogously, you can have a waveguide where you can have two materials, one which has a higher dielectric constant, and the other one which is present on the outside having a lower dielectric constant, epsilon 2. So epsilon 2 is less than epsilon 1. And in this case, if you were to send light, the light would basically bounce within the medium of higher dielectric constant. So these are two ways by which you can make a waveguide. So this is often called as a fiber optic, and this is often called as this is often the way you make waveguides in for microwaves, or also for on PCB traces and so on. So now this concludes the first lecture. So let's continue talking about this in the next class.